Alright folks, welcome. This is your video on the Octet Rule. Nice. So for those of you who are very perceptive, you'll notice that this word octet gives you the sense that we're going to be talking about the number 8 for some reason. Over the next couple of minutes, I'll try to make a case for why the number 8 is important here. And then I'll go on to talk a little bit about how atoms respond when they don't have 8. Of whatever we're talking about. So first things first, let me give you a basic definition of what we're talking about with the octet rule. Okay, so what we see is that atoms are most stable when they have 8 valence electrons. So some key things here is obviously the number 8. We're talking about valence electrons. So the 8 pertains to valence electrons. And additionally, this notion that they are somehow stable. So the idea is that we've talked about stability before. We've talked about the nucleus of atoms and how they are stable under certain conditions. Well, atoms as a whole are also going to be stable under certain conditions. And when I say stable, what I'm really talking about is are they going to react or not? And so that's really the question. Now, you're going to have something that reacts. Something that's stable is likely to not react. Something that is unstable is going to react. And we're going to be kind of unwinding these definitions and these ideas as time goes on. So, to continue, let me explain 8. Why is it that the number 8 is important? To do that, I'm going to show you something that has 8 valence electrons. I'm going to do a little electron configuration for it. So here's neon. And we know neon has 10 total electrons. So that's going to be 1s2, 2s2, and then 2p6. Remember, valence electrons are the number of electrons in the highest energy level. Highest energy level here is 2. So we see electrons here that we got to count, and here. So 2 plus 6 gives us 8 valence electrons. That's where the 8's coming from. What it actually is the valence energy level has a full S and a full P sublevel. So in a sense, it kind of is an expression of how full an energy level is. So with these S's and P's full, remember S can hold 2 electrons, P can hold up to 6, they're full, and that provides for stability in terms of reactions. So at this point, no reacting will occur because it has 8 valence electrons. And again, that's why we call the noble gases the noble gases, because they don't really blend with anything else. It's as if we're in Renaissance times and the king isn't going to talk to some commoner. That's where they're coming from with that. So that's where the number 8 comes from. It's, again, the full sublevels, full energy level idea. All those group 8 elements, all those noble gases, helium, argon, xenon, they're all going to have 8 valence electrons, and if we did out the electron configurations, you'd see the 2 and the 6 here, the configurations ending there with 2 and 6. Now, what happens if you have an atom that does not have 8 valence electrons? Now, if you're, look on the periodic table, there's a lot that don't have 8 valence electrons. For example, you could have something like sodium, Na. Sodium with, 1 more electron than neon does. What's that going to mean? Well, first off, since it doesn't have 8 valence electrons, and if you look on the periodic table, it actually just has 1, 2p6, and then 3s1. That's going to be its electron configuration. It only has 1 valence electron. That's going to imply that it's somewhat unstable, since it does not have 8 valence electrons. There's a kind of a standard response for instability. For something like sodium, right, its highest energy level is 3. And there's 1 electron in it, hence the 1 valence electron. Well, what sodium's going to do, because it's going to be unstable this way, is it's going to react And the way it's going to react is that it's going to jettison this one electron. So what's going to happen is this one valence electron that it does have, sodium is just going to let it go. It just lets it go. I guess I could cross it off, but a better thing might be to just erase it. So what happened is it just literally gave up an electron. What that's going to mean for sodium is where it once had 11, let's see here, 11 protons and 11 electrons. Now it no longer has 11 electrons because it just got rid of one. It got rid of one because it was unstable. It wants 8 valence electrons. So now there's 10 electrons. Look at what's happened now. Instead of having a situation where there was a 3s1 on the end, now we have the highest energy level being 2, and it has now 8 valence electrons. So by getting rid of that one electron, it actually ends up with 8 valence electrons. But what it also ends up with, if you look down here, if you have 11 protons and 10 electrons, that's going to give it a charge. Charge is a function of the imbalance of protons and electrons. So 11 protons minus 10 electrons gives it a charge of +1. So what we'd actually have here is Na+. That's what this technically is going to be an electron configuration for, is Na+, where it has 11 protons, but now 10 electrons. But here's the kicker, is that it has 8 valence electrons now. So as an ion, there are 8 valence electrons. One more example, and then that'll be it. So you just saw me do sodium and how it kind of lost an electron here. I'm going to show you another one. Let's see. Let's try to keep it right around neon. I'll do fluorine. So here's fluorine. Fluorine is right next to neon on the periodic table. That's 1s2, 2p2, 2p... Whoops. By that I meant, of course, 2s2. Momentito. Alright. So we have our 9 protons. We've put in 9 electrons to match. And we see that this guy has 7 valence electrons. But that's not going to be super stable because it wants 8 valence electrons. So you saw how, in the previous example, sodium did something very simple. It dumped its 1 extra electron to get 8. Fluorine's going to do something different. Fluorine is actually going to get some other electron. So it's going to add an electron. It's going to somehow grab on to an outside electron and draw it in. So what I'm going to do right now is show you something slightly different. This is going to be fluorine after, check it, after it's pulled in an extra electron. It doesn't have 9 electrons now like it did at the beginning. It doesn't have 9 electrons anymore. It actually has now 10 electrons. So what it did is it grabbed an extra electron. If you look, the highest energy level now is 2. Well, I guess that's still the case. And if you add up the valence electrons, it's 2 plus 6 is 8. That's going to give you your full 8 valence electrons. So that's going to make it very stable. In the process, we see that, okay, if it originally had 9 protons and 9 electrons, now it has 9 protons and 10 electrons instead. There's 1 more electron than protons, so that's going to give it a -1 charge. So what we see is that what we've done down here is we've drawn the electron configuration for fluorine with a -1 charge, 1 more electron than proton. So take a moment, maybe look at this again, check over different parts, figure out what I did, and we'll do more on this tomorrow.